Hello and welcome back to my spare bedroom lecture theatre. Lecture 2 of Integral Transforms. We're going to do some groundwork today, essentially setting the scene for Lecture 3, which will give us a proper definition of the notion of a distribution. So remember, at the end of the last lecture, we had the idea that if you took a continuous function and called phi, and you multiply by the delta function and integrated, you ought to get phi evaluated at 0. And it's that idea of multiplying by a continuous function and integrating that we take and we generalize. So what we're going to do in this lecture is we're going to start by defining a class of functions to multiply by, and they're called test functions, and we're going to call them lowercase Greek letters like phi and psi and so on. And we're just going to define a class of those. And it turns out, although we won't go into the details, that the kind of space of distributions you get is determined by the way in which you define these test functions. We're going to take a very, very liberal definition of test function, which lets us do anything we like. Those of you who are interested in the theory of PDEs, for example, partial differential equations, will see that you can explore the questions of existence and uniqueness for solutions of those equations through using test functions and what are called weak formulations in much the same way as we're going to do here. So we define these functions, and then we're going to define a thing we call the action of a continuous function. Could be an integral function, but continuous is good enough for us. A continuous function on a test function. And this is the key. This is the property of a continuous function that we are going to take and abstract into the definition of a distribution. We're going to say that if you take a continuous function f and you multiply by phi and integrate, then what you get is a number. So this is a map. It's a map which takes continuous functions and turns them into numbers. It also takes test functions and turns them into numbers as well. So it is the action of a continuous function on a test function. And this map is what is going to be used to define a distribution. Sounds surprising that we can define a thing that looks like a function by a thing that looks like a map. But now think about it this way. If I take all sorts of functions phi, and I multiply my f by them and I integrate, then that really ought to tell me what f is. It ought to let me define a function by knowing its weighted average against all of the test functions. Then we're going to define distributions by saying, well, we don't just have a function here, we don't even think about an integral. We just say, we'll have an action. And we'll work out some properties of this integral, which we can then just assume or define for the properties of this action, and that will define our distributions. It's a very mathematical thing to do, not something maybe that we're terribly used to doing in the second year of your course, but nonetheless, this is what we do. And we've seen one example already. Phi maps to the action of delta on phi, which is phi of 0. So you start with the test function phi, you take the action of the delta function on it, just tells you phi at the origin. And if you think about it, that's entirely consistent with the idea that the delta function was 0 everywhere except at the origin, and all of its mass was concentrated there. So the only piece of information about phi that could possibly survive is its value at the origin. And we define the delta function so that the action is exactly that value. And then we're going to do something even more possibly outrageous. We're going to define the derivative of a distribution. And to do that, we're going to start with this idea of an action for a smooth function defined by multiply by the test function and integrate. And we're going to use the integration by parts formula to say, if you want the action of the derivative f prime on phi, the integral of f prime phi, that's f phi between minus infinity and infinity, minus the integral of f phi prime. So that's minus the action of f on phi prime. This, of course, is true with some care, is true for ordinary functions, and we're going to use it as our defining property of a derivative. Again, very mathematical thing to do. Choose a property that you would like to survive and then use it as your definition of the wider class of mathematical objects. You'll notice you need to do this calculation, you need that phi of x has to vanish at infinity and minus infinity to make this bit go to 0, and this has to be a test function as well to be consistent with our definition, so phi prime must be a test function provided that phi is. Cup of tea. Mathematical Institute mug. So here it is, the definition of a test function. Phi takes the reals and maps them to the reals. Is a test function if two things. The first is it has derivatives of all orders. That's called being C infinity, and we'll use the word smooth. People use the word smooth for different things. We'll use the word smooth in this course for having derivatives of all orders, but C infinity is unambiguous. C for continuous, infinity for the number of orders of derivatives. So that's the first thing. It's has derivatives of all orders. And then the second thing is there is an interval in the real line such that phi of x is 0 outside that interval. So you have a minus capital X to capital X interval in which phi might be non-zero, and outside that it is 0. So 0 all the way along, and then it does whatever it does, but it's 0 outside a finite interval. This is called having compact support, and if you haven't heard the word support before, in the footnote there, the support of a function is the smallest closed set containing all the points where it is non-zero. So you take all the points where it's non-zero, and then you take its closure, or you take the smallest closed set containing it, and that is the support. So this automatically makes phi go to 0 at infinity, because of course it is 0 at all large values of x. And it automatically makes phi primed a test function, because if phi is C infinity, then phi primed is C infinity, because you differentiate something that's infinitely differentiable, you get another thing that's infinitely differentiable. And if phi is 0 a long way away, then phi primed is also 0 a long way away. And we'll call this space of test functions D, although we shan't be using the notation very much. We don't really need to know very much about these test functions. The great thing about test functions is that you never need to do any direct calculations with them. You just need to know that they have these two properties, and you need to know that they exist, and that's what we're going to do next. And we're going to start showing that test functions do exist with a very famous function indeed. This capital phi of x is 0 if x is less than or equal to 0, and e to the minus 1 over x if x is positive. I'm sure you've seen this function in your real analysis, because it's the classical idea of a function which has a Taylor series at the origin, and that Taylor series, every term in it is 0, but the function nevertheless manages to crawl off the axis, even though all its derivatives, the limit as x tends to 0 from above of all the derivatives, is 0. How do you prove that? It's very simple. The derivatives exist and vanish at the x equals 0, because when you work out any derivative of this, if you think about it, you're going to get some horrible polynomial in 1 over x multiplied by e to the minus 1 over x. And the horrible polynomial will come from differentiating that e to the minus 1 over x here in the exponent, and then for higher derivatives it will come from differentiating the result of that, which multiplies your e to the minus 1 over x. You can see how that works. Just write down a couple of derivatives and you'll see what I mean. But what you know is that although 1 over x goes to infinity at the origin, e to the minus 1 over x goes to 0 much faster. This is the same as our normal random variable example, in fact. for non-zero x. To see that, you just put y as 1 over x, so that y goes to infinity is the same as x going to 0 from above. And then you have things like y to the m over e to the y. And you can do that by L'Hopital's rule if you want, or you can just observe that in the power series for e to the y, there is a term y to the m plus 1 over m plus 1 factorial, and a whole lot of other positive terms, and so this is less than y to the m over y to the m plus 1 over m plus 1 factorial, that term you pull out of a power series for e to the y, and that goes to 0. Lots of ways of doing that. So this is, in real analysis terms, a very good function, example of a function, and what it also tells you is that in real analysis, a function is not completely defined by its Taylor series. In complex analysis, of course, you know that's true. In complex analysis, if a function has a Taylor series or a Laurent expansion, then that defines it uniquely. This function e to the minus 1 over z, of course, has an isolated essential singularity at the origin. They're very interesting isolated essential singularities. There are lots of nice theorems about them. For example, if you have a function like this with an isolated essential singularity at the origin, you take any epsilon neighborhood of the origin, the function hits every single value in the complex plane within that neighborhood infinitely often, with the exception of just one, not always, but with the exception of at most one. That's called Picard's theorem, and it's a really weird theorem, but it shows you the difference between complex analysis and real analysis. What's the exceptional value for e to the minus 1 over z? The value that e to the minus 1 over z never hits near the origin. You can work that one out. Anyway, this function isn't a test function, and because it doesn't vanish at infinity. It goes to 1 at infinity because e to the minus 1 over x, the minus 1 over x bit, goes to 0. But if you simply take it and you flip it around x equals, you move it over to x equals 1 and flip it, then multiply it by itself, so phi of x times phi of 1 minus x, you'll get a thing which looks a bit like this. Goes up off the axis with all its derivatives continuous here, reaches a maximum value, and then comes back down with all of its derivatives continuous here, and it's 0 outside of that interval. And that is a test function. Obviously, there are millions more, lots and lots of ways of constructing test functions, but all we really need to know is they exist, they have compact support, they are C infinity, and there are lots of them. Now, this theorem, theorem 8, tells us that if we know the action of a function on every test function, then that function is specified uniquely. It's not actually a very helpful way of specifying the function, because if you know the integral of f multiplied by that test function we just looked at, or by any other test function, or by a whole collection of these test functions, you have no practical way of recovering the function. You can't work out what that function is, and therefore you're no further forward. It's not like, say, a Fourier series, because in a Fourier series, if you know the Fourier coefficients, you can recover the function by just summing and adding all the Fourier coefficients multiplied by the relevant exponential functions. So it's not a practical representation, but nonetheless, what it tells us is that if we know the action of the function on all test functions, then the function is determined uniquely. The way the theorem says this is it says that if the action of f on phi is 0 for all test functions, then f itself must be 0. But then it's a short step from that to say that if we have two functions with the same action on all test functions, f1 on phi, the integral of f1 times phi is equal to the integral of f2 times phi for all test functions, then f1 must be equal to f2. And why is that? because we simply subtract f1 minus f2 on phi integrated against phi would then be 0. So how do we prove this? It's a neat little proof, and I will give it. We're not going to do too many proofs in this course, but I'm going to give you this one. Those of you doing calculus of variations will see a rather similar one later on this year. And the way it works is we say, suppose that for a contradiction, we're going to go for a contradiction. Suppose that there's a point A where f is positive, so there's A, and there's f positive at A. It could be negative, but positive's easier to draw the picture. Then because f is continuous, we know that it doesn't go far from the value f of A. And in particular, there is an interval, a minus delta to a plus delta, in which the function is strictly positive. It doesn't hit 0, doesn't go below 0, it's strictly positive. And that's just the standard definition of continuity. So all I do is I produce a test function, which is the function we had before, just moved around and scaled so that it fits onto the interval a minus delta to a plus delta. So it goes from 0 strictly positive and then hits 0 again when we get to a plus delta. And then I multiply the two, and obviously I've got something positive. So the integral from a minus delta to a plus delta of f of x phi of x, well, that's the same as the integral minus infinity to infinity, because this test function is 0 outside of this interval a minus delta to a plus delta. The integral is positive, but that contradicts the assumption that the action of f on phi is 0. Therefore, f can't be positive, and similarly can't be negative, and therefore f is 0. Now, we're going to introduce one more thing, and this is the notion of convergence of sequences of test functions. So you will have got the impression by now that there are many kinds of convergence. There's, in particular, the kinds of convergence that you use a lot in your analysis are pointwise convergence, which says that a sequence of functions converges at each point, and then uniform convergence, which is a stronger form of convergence because it says not only do you converge pointwise at every value of x, but also you converge at essentially the same rate. In other words, if you're given an epsilon, the difference between the sequence and the limit is less than epsilon for all x, not just at a single point for large enough n. You know the difference between pointwise and uniform convergence. Well, we're going to define, because we're starting off here, we're going to define a kind of convergence which is even stronger than this. And because it's such a strong form of convergence, we will be able to very easily prove a lot of very powerful results with it. And you'll see one or two of these in the problem sheets. Definition: the sequence phi n of test functions, so this phi n of x are test functions, converges to 0. So two things have to happen. The first is phi n of x is 0 for all n and all x outside some interval in the I in the real line. And what that does is it stops you having one of these silly examples where your test functions move along as you change n and they go off to infinity, so there's always somewhere where they're non-zero. So that just keeps them within reach, as it were. And then the second thing is, for all a, this is the really strong bit, for all k, the kth derivative of phi, so this is notation, k up here means the kth derivative of phi n tends to 0 uniformly as n tends to infinity, and that uniformly will be on this interval I in the real line. So, as you know, you can, if you differentiate sequences of functions, you don't necessarily get uniform convergence of the derivatives. Well, we're insisting it does happen for this kind of convergence, and that's why I say it's a very strong form of convergence. And then we'll say that phi n tends to phi if their difference tends to 0. And just a little note, which is that the definition ensures that the limit function phi of a sequence of test functions is itself a test function because of standard results for uniform convergence of phi and all its derivatives. So, what we've noted with these things in mind, we can now go back and look at the action of a locally integrable or continuous, if you like, function on a test function. And what we'll do is we'll pull out a couple of properties of that which we'll use to define our distributions. So the action was a map from the space of test functions to the real line, real numbers, which says take f, multiply by phi, and integrate. So what properties does this map have? Well, an obvious one is that it's linear. If you take the action of f on a linear combination a phi plus b psi of test functions, then you have a times the action of f on phi plus b times the action of f on psi. So that just simply substitute this into here, and you'll see that this pops out. More subtly, it's continuous. Now, by continuous, what I really mean is that if you have put a small input, then you get a small output. That's roughly what continuity means, or a small change in the input generates a small change in the output. And what that means formally is that if phi n is a sequence which tends to 0, then the action of f on phi n tends to the action of f on 0, and that's 0. We know that's 0 by standard uniform convergence results. So this map is linear and it's continuous, and those are the properties we're going to use to define our distributions, and we're going to do that in the next lecture. So I'll see you then.